Question 4 from the 2025 Higher Physics Examination from the SQA Paper 2. The theory of special relativity states that the measurement of time for an observer moving at a high speed is changed relative to a stationary observer. And for 1 mark, we're asked to state the name of the effect. And the name of the effect is going to be just simply time dilation. So we'll mark that in, and that will give us our 1 mark. The word dilation means almost expand. Think of the fact that when your eye goes into darkness, the pupil dilates, it gets larger. So what we're saying here is time dilation is that the time measured by the observer is larger than the time measured by the astronaut on the spacecraft. Now, that's what part B is all about. It says a spacecraft is travelling at a constant speed of 2.29 times 10 to the power 8 metres per second relative to a nearby planet. A technician on the spacecraft measures a time interval to be 245 seconds. And for 3 marks, we have to calculate the time interval as measured by an observer on a nearby planet. Now, to do that, what we simply do is we have a little diagram. I always insist on having a diagram. It's maybe not as complicated as this, but a quick sketch to see what's happening and fill in all the necessary data we have. The spacecraft, first of all, is moving at a speed of 2.29 times 10 to the power 8 metres per second. And the time measured on the spacecraft, which is called the proper time measured by the astronaut on it or the technician on it, is going to have a time of t equal to 245 seconds. Now, the observer on the planet, he's going to measure, or she's going to measure t prime, which is going to be the observer's time. So we can now work out the formula from relationship sheet. We know that t prime, the observer's time as he observes it, is equal to the proper time measured on the spacecraft by the person in the spacecraft's frame of reference, divided by the square root of 1 minus v upon c all squared, where v is the speed of the spacecraft relative to the stationary planet, and c is the speed of light. Now, the v upon c part can be simplified because we can write v upon c as follows. V is going to equal to 2.29 times 10 to the power 8 metres per second, and we divide that by 3 times 10 to the power 8 metres per second. And you can see things cancel out, times 10 to the power 8 times 10 to the power 8 metres per second, and you're left with just simply 2.29 divided by 3. So we can put in our values now. T is the proper time measured in the spacecraft, 245 seconds. And we're dividing that by the square root of 1 minus, and it's going to be bracket, v upon c. We've now ascertained that to be 2.29 divided by 3.0. And it's going to be squared. Now, all we have to do is take our time, put that into our calculator, and we end up with the time measured by the observer to be of the value of 379 seconds. And you can see that the observer measures it to be 379 seconds, whereas the spacecraft 2.45 seconds. So really the time has been dilated, as I've asked in the first question. Question 4 continued part C. A student makes the following statement regarding special relativity. Train drivers who travel at speeds of 80 metres per second over large distances will have to reset their watches frequently as they spend so many hours travelling at high speeds. State whether the student is correct, and we have to justify our answer for that. Here's a picture of the train driver and an inspector on the platform. The inspector is at rest, and the train driver is moving in his reference frame, which is the train. Now, just like the last question, we can put in our letters. We can say that the train driver measures a certain time, maybe from one station to another, and he measures that as proper time t in his reference frame. The observer or the inspector on the platform, they measure time t prime, because they measure this thing that this train is moving past with a speed. But here comes the crunch of the matter. The speed of the train moving past relative to the inspector is 80 metres per second. Now, that's nowhere near the speed of light. So we only get time dilation when we get speeds relative to one another which are the fraction speed of light. And this can be summed up with this graph here, which you could reproduce to justify it. And there's the graph here. You can see that the relative speed between the train driver and the inspector, you can see that even for up to about 30 or 35% the speed of light, you're not going to get any effect on the time dilation. It's only when you get to speeds, relative speeds, which are fractions of the speed of light, very high fractions or very high percentage of the speed of light, will relativity effects come into play. So the student is wrong, because at our speeds, at everyday speeds, then relativity effects do not come into play. It's only when the speeds become much, much closer to the speed of light, then you'll get things like time dilation taking place. So for all intents and purposes, the train driver and inspector, they measure the same times. So the student is wrong.